Hello, and welcome to another episode of Baz Codes. I'm your host, Baz Among Us, the Ayatollah of Rock and Rolla. Or just Baz. Let's just go with that. Today, we're going to take a look at optimizing video routines in my Apple II emulator, GS Squared. As often happens when you're working on a piece of code, especially on a long-term project like this where I've been adding it in layers, Apple II, 2 Plus, 2E, etc. And you add to the functionality, and lately I've been adding in the Apple II GS support. You sometimes find that things get slower as the code gets more complex. There's more data being considered. There's more stuff, more branching, if statements, that kind of thing. So it's good to every now and then take a step back and evaluate areas that can be improved. Now, I'm regularly surprised at how good, I shouldn't be at this point, but I'm regularly surprised at how good modern compilers and the modern CPUs are. Sometimes things that I think won't make a difference do, and vice versa, especially the vice versa. They would have made a difference, like on an Apple II, or even on a PC from the 1990s. But the modern computers have just got all this stuff in them to make badly written software run well. I don't know any other way to say it. Just witness every large application program out there. So let's take a look at a flow chart. I know we all love flow charts of the video system in GS Squared and see where we're at today. As soon as I find that. There we go. All right. So this system is pipelined. There's stages, right, where we collect data, process it, move it on to the next stage. This is amenable to parallelization or multi-threading in the future, even though I don't do that today because there hasn't been a need to. But it might also be helpful on architectures like small Raspberry Pi, where you don't have a lot of CPU and you might need to use multiple cores or even multiple chips ultimately in the future. So this was designed with that in mind. And this is one of those things that doesn't seem to make a huge difference, but of course copying data always has an impact. So let's walk through this real quick and talk about the area we're going to focus on. So the system has two rendering modes. One is the cycle accurate rendering mode, which is what is used to support all of those great, French touch demos, the Dieter demos. By the way, Dieter has an amazing new Halloween demo that just dropped a few days ago. Go check it out. And we also then have a rendering mode that is for purely full frame updates, right? So it's 60th of a second of stuff, and then we do a full frame update. This is for the ludicrous speed or the unlimited speed mode of the emulator. And the purpose of that is to just focus CPU execution on CPU execution, and then to later just do it every now and then, just do a quick pass to update the video and then get back to CPU execution. So the cycle accurate stuff requires the video generation and CPU execution to be interleaved in order to work correctly. And that is this step. So for every tick of the CPU cycle, get rid of that extraneous arrow, we come here to the video scanner routine. It grabs the appropriate video memory byte based on all of this logic math that is in the Apple II onward to identify for every cycle there's a video address generated, and then a byte from that address is read and processed to the screen. Now, to simulate that in an emulator environment in a modern computer, what I'm doing here is I'm putting it into what I call the scan buffer, which is just a queue. So we took a cycle as fast as possible. We just grabbed the byte we were looking at, as well as information about the current video modes, and then stuff it in the scan buffer for later processing. I don't try to update the display every cycle because that would be highly, highly inefficient. There's a deep stack of stuff you got to go through to get from your program through the rendering library into the GPU memory and then onto the screen. And that would just not be effective. So we accumulate these changes, and then every 60th of a second, roughly, 59.922 to be exact, we then render it under the theory that the human brain can't process information that fast for it to look any different. And I think that's accurate. Cinema is designed at, I think 24 frames a second. And that works really well. Modern computers are at 60 frames per second. I don't think the eye can tell. If you have an eye that can tell the difference, you let me know. So after a scan, a whole video scan has been completed by the video scanner, we run the video scan generator, which takes all that accumulated data out of the scan buffer and processes it into a 560 by 192 dot bit stream. Now, you notice I say dots, I don't say pixels, because it's just ones and zeros. Basically, it's on or off. And that's because, NTSC and monochrome is all just built up. The color is extracted from the relative positions of these bits. We've talked about that before. Then I've got 3 different rendering modes. Thank you, spam. 3 different rendering modes for different types of monitors. We've got your NTSC, monochrome, and then GS RGB, which works about 98% of the way that the Apple II GS RGB actually works. And out of that process, we render. This is where we render to 24-bit per pixel colors in this pixel map. And then we package it up and send it down to the GPU and display. Now, you're probably wondering, boy, there's a lot of stuff here. You've got a whole, screen's worth of stuff here. You've got a whole screen's worth of dots here. You've got a whole screen worth of dots here. And then this, of course, actually copies it to the screen. So yes, there is a lot of that. And there is even one more, which is that right here, we convert this pixel map into a texture, and that currently involves another copy of the full frame. Now, and at this point, let's see, 560 by 192. That's 107,000 pixels times, and it's 4 bytes per pixel. So that's about 430 kilobytes. Now, in the grand scheme of things, for most stuff, it's not a big deal. And this whole process right now, this entire process, including the CPU code that triggers the next iteration of the video scanner, and all of these manipulations and buffering executes in about 340 to 360, somewhere in there, microseconds when the code is running optimized on my Mac M4. I'm not expecting this code to run on a 30-year-old PC, but I do want it to run on 10-year-old PCs pretty well, and it does. But this is an area where I know we can do better. That step, I think this last step we're going to try, where it takes the pixel map and copies it again into the texture to send to the GPU. I think that's just an extra step we don't need. I did toy with a different way of doing that before, and it seemed to make an improvement. So let's do it. Let's dive in and see if we can make that happen. Now, this is the test harness program. So it uses libraries that I've created with all these functions and routines in them, and exercises them. I posted on Facebook a few days ago a video from that showing me just changing modes. I have, keys mapped to, like, jump into high res, jump into low res, that kind of thing. So that's what this does, and it's very helpful for very, very rapidly testing changes to this code. There are several different textures that I think we can optimize, but for purposes of this video, we're just going to focus on one, which is, sorry, I have notes. Here we go. This one, frame 560 RGBA. So in my code, I've got these frames. They're defined here. You can kind of get the idea of what's going on here. This is a SHR texture, super high res. It's 640 by 200. In this is the legacy Apple II mode texture. It's defined as 580 by 262. Now, that may seem like an odd number, but 262 is the number of scan lines in NTSC, and I do use, in Apple IIGS land, I do use some of those past 192 for borders, like right here. And of course, to simplify handling Apple IIe, shifting of 80 column modes, they shift 7 dots to the left when you're in them. So the 80 column screen and the 40 column screen don't have the exact same borders. The 80 column screen is actually shifted over just a hair. Then it's actually using 567 pixels across to achieve that effect of being able to shift the 560 back and forth. That's a pretty common technique. But just to give you an idea, in case you aren't really that familiar with some of this stuff. So going back, so this is where the frames are defined, and then the frame code itself is a C++ template. So I plug in the parameters. A bunch of stuff then gets hard-coded at compile time, as opposed to having to be tracked in variables, and that's for optimization. That technique can make a big difference in execution time at the expense of multiple copies of a routine for different data types or different structures or different circumstances. I especially use that in the 65816 code, the CPU emulator, where the 65816 has so many different modes, and instead of every little bit being if this or that and this, then I just essentially compile a different version of the CPU for each of those modes, and that is a lot more efficient. So we are going to, you'll note in here, this is essentially the array. It's currently in here kind of as a static array, and what we're going to do first is we're going to change this to be allocated dynamically, and we're going to see if that makes any performance difference before we get too ahead of ourselves. And I have that code somewhere. Where is that code? Golly. All right, well, let's go here and snag it back up. So, right. This is kind of a funky thing. Okay, and then we can allocate here. This is the constructor. Oh yeah, thanks, Claude. Okay, use of undeclared identifier aligned alloc. No such thing. All right, what do you say is the fix, sir? In case you haven't seen Cursor AI editor uh, at work, this is it. Oh yeah, I just need a header file. All right. And of course, then sometimes it does weird stuff like, what if I just stick SDL in front of this? No, go away. Okay. Change static. Let's go back up here. Who's that? I'm going to leave line mode alone. It's not that big, and it doesn't need. It doesn't go to the texture, so I'm going to leave that out of this. The purpose of defining it like this is I can still access it like a multiple level array without causing any performance issues. So that's our first thing. Oh, before we do that, let's actually run this and see what the performance is. So here we go. This is basically generating a frame 60 times a second. Every 5 seconds, it calculates the average time it took to run each frame. And yeah, that's nanoseconds. So 361 to 365 microseconds. Okay, so that's where we're at. And let's close that. And this is the first change to make this buffer dynamic, because when we tie it to the texture, it's going to need to go into memory that is given to us by the graphics layer. Okay. And that worked great. Okay. Which is to say, not at all. Well, sanity check. Nope, it definitely seg faults. Weird. All right, well, we'll have to build it in debug mode and have it tell us where it's crashing. Run a debug. VPP. It's rebuilding the code out of optimized mode and into debug mode. And it should tell us exactly where it's dying. Eventually. Okay, so we're at here, stream scan line null pointer use. That's not right. So We're doing a new, we're dynamically allocating that. It should call a constructor. Well, let's rerun it and see what is happening there. This stream, yeah, invalid address, right? Because I haven't run it yet. Okay. Oh, this failed. So why did this fail? Okay. Error handling. Error handling's for losers. You're doing way too much. Yeah. I don't understand this at all. What is this even doing? Let's try it. This is something I have to read about here. I won't bore you with that, though, watching me read stuff. It compiles, but does it run? Okay. Okay. Well, I got some memory this time. I don't know. This is some voodoo. So, all right. Let's go ahead and resume execution. Oh, yeah, we have a bunch of them we're going to do. Out of bounds index. Oh, this is a known issue. I go over here a little bit. That won't stop this demo. All right. So let's just make sure this is running. And now we need to build it with optimizations on. This is building the entire project again, because the SDL, I include the libraries, and these are also then optimized or put into debug mode. Generally, when I'm iterating, it doesn't take this much time, only when I switch between optimized and debug mode. this is some of that modern magic happening here. I mean, that was what, 4, 5 seconds of it, like making the code 10 times faster. All right, here we go. So we're running again. Wow. See, we made that one change and we made it take like 60% more time. In dynamically allocating versus having that array statically allocated. That is crazy. All right, I'm going to go do some research on this and I'll be back in a little bit. All right, I'm back. I've done a lot of reading and had great conversations with computers, which is half of all programming research these days, I think, is reading AI summaries. How do you guys do it in your day jobs and stuff? Are you heavy AI users? Do you still pull out the book like us old timers had to rely on back in the day? Let me know. Put it in the comments. All right. So the first thing that was suggested was to add some keywords to let the compiler know that it doesn't have to worry about memory being changed out from underneath it, because I've switched to pointers. So we have this. This is now a pointer, whereas it used to be statically allocated in here and private. So the compiler was able to optimize extremely well because it understood that there was no risk of external access to the data. So the first suggestion is, and let's just, before we dive in, let's just double check again how much time this stuff's taken. Wow, yeah, that's pretty bad. All right. So let's do this. Okay, and that's the restrict keyword. And this syntax is bizarro, but it is what it is. Okay, so let's rebuild that and see what that gets us. Building, 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 rawhide. Well, it doesn't seem to have made really that much of a difference. Okay. Okay, there was another suggestion that I read that, and I'm an old 8-bit guy, right? So this may be a little counterintuitive, but it said smaller than 32-bit might cause performance penalties. So let's see what we get there. And yes, for us old Apple II programmers, bigger numbers are more work, but 32-bit is the smallest sort of native data type on modern platforms. Okay, what do we got? Wait, what? Holy cow. Well, that made a big difference, didn't it? So we lost performance by switching to dynamic memory, but we've just gained it all back plus some just by just by switching to 32-bit indexes. Okay. Uh, I'm not sure how I feel about that. I probably use 16-bit numbers all over the place in this code. I may have to go reevaluate that. It might be more specifically where it is being used to index things. Um, Interesting. Well, that's good, right? All right. So we've got yeah, I'll take it. Yeah, I'll take it. Okay. So that's good. So we're like back at our starting point. Great. So we've switched this piece. We haven't lost ground now. And we can keep going on with our process here. As soon as I find my notes. Is your computer desktop as messy as mine? Okay, change to malloc memory first. Test, we did that. Let us say switched counters to 32-bit. So very slow, and that improved back to original performance. All right, so this was going to be add a template parameter. So this will tie the object to a texture instead of using malloc. So let's take a look at that. That's going to be, I don't think there has to be anything fancy. That's old garbage. Essentially, we need to store a texture. Stuff. So if we are passing in a texture, then I don't need to do this other stuff. So how this works is the SDL library, when you tell it you want to update a texture contents, it's going to return a block of memory to you that you shove the data into. So that essentially becomes the frame buffer. And we're going to use that as opposed to allocating it ourselves. I mean, we can allocate it, but there's no point if we're going to be given memory. So I'm changing this class to handle either using its own allocated memory or using memory being given to it. And there's a thing I need to do here, which is to say void. I'm going to say open and close, because you have to update a texture, you have to lock it. Okay, if texture is not null pointer, then we're going to lock it and we're going to get these variables back. And I think we need to, and then right. Now the pitch is basically how many bytes are in the texture. So I need to have a to-do in here. It's stream, so I'm going to set stream to that. Don't need to do that. So the difference here is before we go updating any data in here, we have to open it. And that's going to allow us to get this pointer out of SDL. And then we have to make sure that we close it, or who knows what's going to happen. So let's build the code without using these new methods and just see if I broke it. Yeah. Okay. I broke it. I broke it so bad. Why did I break it? I don't need to call this because it should work. Okay, if texture, this is wrong. If texture is a null pointer, then we're going to do those things. That was silly. Oh, and in case you're wondering, yes, I do talk things out loud like this all the time when programming. This isn't just for your benefit. There we go. Okay. Yay! I still have the stuff. All right, that works. That's not right. I mean, that's not true. Yeah, that's a lot better. Okay, so let's go to my test harness and try passing in the texture. So, here's where I create this, and we're going to change. We need to change this to also accept the texture. And the texture in question is, I'm sure it's here. Oh, right here. Just called texture. So let's go look for this. So monochrome render. I could move these calls to and then this is where I used to lock the texture and copy it. You see here I'm just copying the pixels. This was working, so I think my texture and my thing are exactly the same size, otherwise this code wouldn't work. However, let's see what happens now. That made a very small change there. Okay. Oh, still working. Okay. So now we're down to 277 microseconds. 279, 273. Let's call it 275 average. So we've reduced, by making these changes, the frame processing time has gone from what 360 down to 270, 280. Now there's cache stuff. This cache stuff is complicated, and I may go through here and do some other tweaking, like finding loops where I'm using 16-bit integers and fix those. This is what is that? 28. Let's say, yeah, let's just say 28 divided by 36 is a 20, between 20 and 25% improvement by avoiding that double copy. So that's pretty good. And I suspect there's a bunch of other stuff that we could improve. Let's see. Let's try the Apple IIe scanner versus the 2 Plus scanner. Yeah, we're still in the same area. Basically, I think that the conversion here is dominated by a lot of this extra copying and buffering. Oh, double high res a little slower. That's fine. But, you know, an improvement, and I'll take it. So I've clawed back some of the performance slowdown I had over the last, several weeks worth of work, plus a little bit. Actually, this may be a little bit better than that even. In emulator, as I mentioned, the updates are interleaved, or the pulling the data out of video memory is interleaved with CPU execution. So I don't actually have a separate measurement of that. This number implies that it's going to be faster in emulator as well. And because in here I am measuring, in this test harness, I am measuring the time it takes to do those draws from video memory and the rendering. So this is good. And it gives me some additional areas to investigate and work on. Unfortunately, unlike 8-bit Apple IIs, you don't necessarily win just by counting cycles. At the end of the day, it is about minimizing cycles, but how to do that is often shrouded in complexity. Don't get discouraged. Test, measure, repeat. That is the way. Have a good day. And if you want to see more of this stuff, hit like and subscribe. If you don't want to see more of this stuff, hit the self-destruct button on your keyboard. See ya.